you're just joining us, we're going to get started in just a minute or two here. Almost 9 o'clock, but not quite. I'm just going to get a couple things set up here. So as you're getting ready to go, don't forget that you can jump into either the stream chat here on Twitch, or you can also feel free to jump into the Slack channel and use those as ways of asking questions and sort of just getting the most out of these streaming office hours as you can. If you're watching this after the fact, then bear with us as we just get started here. I just need a couple minutes before we're going to be ready to go. When we started the stream today, it was super bright and sunny. It's not so bright and sunny right now, so I'm going to turn on some lights. There we go. I think we're doing a little better. Just get adjusted here. Turn up the electronic lights too. Okay. All right. So again, if you're watching in Twitch, feel free to drop in your questions, your comments as we go along. They will actually show up here in the stream. So that's one way of interacting with what's going on here. The other is to post your questions, your comments in Slack. This will work if you don't have a Twitch account, but you're watching anyway. Feel free to do that. So I have kind of a couple of goals, I guess, for our streaming virtual session today. The first is to get us back into Cayley table land a little bit and look at some things that we can do with Cayley tables that help keep us connected with the definitions of a group. So that's kind of step one. Put that here on this first screen. Cayley table and the properties of a group. So that's step one. And then step two is I also want to go back into sort of what we talked about in our last streaming session, which is the kind of about the craft of discovering and then communicating a proof. So how do we How do we think about the process of discovery versus the process of communication in writing a proof? And so I want to do just a couple more proofs. And I'm going to bring in to the session today the definition, a proof that a certain group is abelian. Helps if I spell the word certain right. Certain G is abelian. And then, I suppose if we have time, I'd really also like to get to a group of matrices. And that group is called GL2Z mod 2. So, one of the big questions in abstract algebra, and we're going to talk a lot about this semester, is if you give me a bunch of elements, so you just give me a set of elements, can we make a group out of that set? Right? Can we define an operation? In other words, can we draw out a Cayley table with those elements that's going to satisfy everything that we need a group to satisfy? And that's a big question. It's not a question that we can answer in 1 week or even in 1 month or in 1 unit. In a real sense, that's a question that's even bigger than our 1 semester. Our culminating event this semester, sort of what we're working up to the whole time, is going to be a classification theorem for finite abelian groups, which means we're going to understand what are all the different ways in which we can build a finite group with a given set of elements when that group is abelian. The question of how to do that when the group is not abelian is a much, much larger question. And that's a question that mathematics didn't resolve until about 10 or 15 years ago. I was in graduate school at the time when the classification theorem for all finite simple groups came out. And the simple groups being the building blocks of larger finite groups, it then implied that we understood pretty much completely the structure of all finite groups that there can be, whether they're abelian or whether they're not. So we handle the abelian case this semester, but the non-abelian case is much bigger, much more intricate, and the proof for the classification theorem of finite simple groups is like, it's book length. I haven't read it, but it's very, very detailed, very technical. So all of that was a roundabout way of saying that one of the ways that we can think about how to create new groups that might not be the obvious examples that we've already seen is to think about how do groups of matrices behave, right? Matrix multiplication being one of these first operations that we learn coming up through mathematics that is not abelian, doesn't have the commutative property. When you multiply matrices, the order in which you multiply them matters, which is why matrices are really useful tools for creating new algebraic structures. So let's go back to Cayley tables, just to kind of get us started for today. And by way of doing this, I want to use that question, that big question about how many groups can we make from a given set of elements. And we'll use the Cayley table to address that question for the case n equals 3. So if G has elements A, B, and C, let's say. So somebody comes up to me on the street and hands me this set of 3 elements. And they tell me, make a group out of this set of 3 elements. First of all, can we do it? Can we make a group with these 3 elements? And if it's true that we can make a group with this set of elements, in how many different ways can we do it? And because this set of elements is so small, using a Cayley table, coming up with a Cayley table, is actually a pretty practical way of figuring out the answers to these questions. So let's just start by doing that, because we know that a Cayley table for a group that has these 3 elements is just going to have A, B, and C going across the top, A, B, and C going down the side. We'll put our fictitious operation over here. I'm going to write it as a circle today instead of as a dot. Doesn't matter. We're defining this operation in whatever way that we need to. So It doesn't have to mean anything. That's what's great about abstract algebra. It's also what's frustrating about abstract algebra, is that it doesn't always have to correspond to an operation that we understand from some other more concrete context coming in mathematics. So it's not necessarily function composition or multiplication of numbers. It's just some operation, some way of turning two elements into a third. Right? And we need, for this operation, in order to make a group, we need for the operation to be associative. We need for it to satisfy the closure property. We need it to satisfy the identity property and the inverses property. So if we think about what those four properties are going to do for our Cayley table, we're going to have to check that associativity holds, again, that any three elements that I choose, if I string those three together with my operation, then I should get the same answer if I evaluate the second pair before the first, or if I evaluate the first pair before the second. Right? So that has to hold if we are building an associative operation. We also need closure. And closure here means that there can't be any way of operating on two of my elements in this set and producing an element which doesn't belong to this set. Right? Every operation of an x with a y belongs somewhere as one of those three elements as well. So closure just means that all the entries in my Cayley table are going to be elements of my group. So they're either going to be A, B, or C in this example. So as I'm filling out this table, I can't put anything other than A, B, or C inside of my table. I need an identity, so this operation has to satisfy the identity property. There exists an E in the group such that X operate E and E operate X are both equal to X. And then I'm sort of running out of room. Let me move some stuff around. We need the inverses property. And that says, for all x in my group, there exists a y such that x operate y and y operate x are both equal to the identity. Okay. So let's take those two properties, actually, and think about what those two tell us about our Cayley table. Okay. So what, if anything, will we see happen in our Cayley table because of the identity property? The identity property says that there's got to be some element. So in our example, it's got to be either A, B, or C that acts as the identity. And whichever of those elements acts as the identity, we will recognize it by the fact that anything that it acts upon is not changed by that action. Right? When I compose any x with the identity, we're going to get that x, and that happens on either side. So the first thing that we might do, if we're trying to make a Cayley table from this set of elements, is let's identify one of my elements as an identity. And because of what we saw in the last couple of videos, the identity element in a group is unique. So I don't have to try to make more than one of my elements fit this mold. So let's just make one of them. And just for simplicity, let's make A be the element that meets the identity property. So that's kind of my choice number one that I'm making in building this Cayley table. Is I'm going to first choose one of my elements to behave like the identity. And if A behaves like the identity, then that means that everything that it operates upon, A operate A, B operate A, C operate A operate B, A operate C, all of those operations need to leave the thing that they're operating on unchanged. And so as a result, that row in my Cayley table and that column in my Cayley table are just going to be repetitions of the header row and the header column in my Cayley table. Right? So that first identification of an identity element already fills in a lot of missing spaces in my Cayley table. Okay, great. So we've met the burden for the identity property. Let's move on to the inverse property and think about what we're going to need to do in order that the inverse property be satisfied. So the inverse property says that every element has to have some element in the group. I was going to say some other element, but it doesn't have to be a different element always, right? There are elements that are their own inverses. But there has to be some element in the group that when we operate on X, undoes X and turns it into the identity. So this just means that every row and every column of my Cayley table needs to have an identity element in it. Right? And since our identity element is A, let me make it a different color here just to sort of cue us in to the fact that this is acting like an identity for us. I need to find an A in every row and in every column. Well, in the first row and in the first column, we're all set. So let's move to the second column. I need to have an A somewhere here in this second column. Let me make a little bit of space over here. Because now we have a couple of choices that we could make. And let's play both of them out to see how they work, or if they work. Since I know I need an identity element here in this second row, maybe my first case that I can try is to put the identity element here. Case 1, B operate B is equal to A. So let's play out those consequences a little bit more and kind of see what happens. If I make that choice, then the question is, how do I fill in this third element on the row? Right? Is that going to force me to fill in this third element in a certain way? So let's find out. Let's go through the different choices that we could make here. On the one hand, if I try to fill in this last element here, this element would be B operate C. I have 3 different ways I could fill that in because I have 3 elements in the group. On the one hand, I could say, well, can I fill in this entry with A? Well, if you're watching the stream right now, maybe you see the problem with putting an A in this slot. What is the problem with putting A in this slot? So remember that our basic definition of group also got us some interesting properties that every group enjoys. Every group has a unique identity element. Every group satisfies both the left and the right cancellation properties. Every group has a unique inverse for each of its elements. And every group has the shoes and socks property, that the inverse of a product is the product of the inverses in the opposite order. And because those things must be satisfied by a group, they must be satisfied by whatever structure that we're making here. And so what you might notice is that if this is A, then that would mean that B operate B is equal to B operate C. But because our group must have the left cancellation property, because every group has the left cancellation property, that means that we could cross these two out and arrive at B equals C, which is a contradiction, because we assume that we have 3 different elements. If I find myself claiming that those two are the same, then I've arrived at a contradiction. So in other words, we cannot put A into this slot. It's not possible, because we no longer would satisfy the left cancellation property, because the left cancellation property would destroy 2 of my elements. It would make them into 1. So we've shown that we can't put an A in that slot of the Cayley table. Let's game out the other possibilities. By the way, the shorter answer for why we can't put an A there is that the uniqueness of inverses guarantees that if B is already the inverse of A, then we can't have a different inverse. If B is already the inverse of B, then we can't have another inverse of B, a different element which turns B into the identity. Right? So we can't put A there twice. All right, what if we try to put B here? Can we come up with a reason that that's not possible? Well, we're not able to do what we did before, right? Because we don't have the same thing on the right-hand sides that allows us to equate these two sides. On the other hand, though, looking elsewhere in my Cayley table, I find out that if C is acting on B in this way, right? If when I apply C to the right side of B, I get another B back, that means that C is behaving an awful lot like an identity element. Right? And sure enough, here in my Cayley table, I also find that B operate A is equal to B. So if I highlight that real quickly and bring that over, now we can make again the same argument that we had made before, which is to say that B operate B, oh sorry, that's not legible. Let me get a better color. B operate A is equal to B. And now we have again the ability to equate these two expressions because the transitive property of equality holds. So B operate C equals B operate A, and then again my left cancellation property would guarantee C is equal to A, but that's a contradiction because again we assume that all of our elements are different. So not only can we not put an A in that third entry, we also can't put a B in that third entry. That means that if it's going to be possible to make a group out of these three elements in any way, then we only have one possible way to do it, and that's to put a C here. So what's the problem with a C? Again, if we're going to try and make a cancellation argument that leads to a contradiction, what we were looking for here, what made their previous arguments not work, when I had an A here, when I had a B here, those didn't work because there was an A or a B respectively on the same row that allowed me to arrive at a contradiction using one of the cancellation properties. The C is not repeated elsewhere on its row, but it is repeated elsewhere on its column. And so maybe that's a clue that putting a C here is going to give me a problem with this entry. Let's try it. So if B operates C is equal to C, let's also key in on this C that lives above it on the same column and write down what that would be telling me. That would be telling me that A operates C is equal to C. And now again, by the transitive property of equality, that means these left-hand sides must be equal to one another. B operates C equals A operates C. And now you can see the problem. Not left cancellation this time, but right cancellation. That common factor of C on the right side of both expressions can be disposed of. And we find out that in this case, B must be equal to A. And we can't have that because we know that our three elements of this group, the three elements of this set, are different from one another. Right? So in other words, there's no element, because again, we have to have the closure property. I can't pull in some brand new thing and try and put it right here, right? There's nothing that I can put in that blue circle that's going to make this Cayley table be the Cayley table for a group, because the cancellation properties are going to be violated. So this case 1 is unsustainable, right? Untenable. We can't actually, therefore, write that B circle B is equal to A. So that choice that we tried to make to get us started is a choice that in every case is going to lead to a contradiction. So that means that case 1 is over. It's impossible for the reasons that we just showed. If I were actually writing this out as a proof, I would put a lot more language underneath that, but for now, we're just kind of doing this as a problem-solving exercise. So if we can't put an A in this spot, what other choices do we have? Well, we could put a B there, but based on the arguments that we've already made, you can see why that would also be impossible. B circle B equals B. Just to kind of talk through that real quickly, this would mean that B acts like an identity element, right? Because it's not changing B on either side, but we already have an identity element A, and so that's going to be violated also. So without going into the detail, you can supply that if you'd like. We'll just say, because of that uniqueness of identity property, or equivalently a cancellation property, writing a B in this middle spot is also impossible. So we only have one road out now. Our third case is to let B circle B equals C. So if I put a C here, that doesn't raise any immediate red flags because C is there's no other C on the row or the column that I've placed it yet. Right? And based on the arguments we've already been making, we know that whatever we fill in this circle cannot be another C, because then the cancellation property is going to collapse this B and this C. It can't be a B, because then the cancellation property would collapse these two. The A and the C would have to be equal. And so the only option for what I can put here is an A. And then we should check that if I put an A here, that we're still in good shape, right? That B circle C is equal to A, and there's no other A on its row or on its column that's going to lead to the collapse of two or more of the elements using the cancellation property. So we're safe putting an A here. But now, if I've put an A here, we can fill in the rest of the table. Because the argument that we've been making so far is that we can't repeat any element in a Cayley table on the same row or on the same column. Because if we do, then either the left or the right cancellation property is going to collapse two or more of the elements in my group and say that those elements must be equal to one another. Right? So if we can't repeat anything on any row or on any column, then all we're doing is we're playing Sudoku with this Cayley table. Right? Sudoku is the game with the digits 0 through 9. You have to arrange them in a big 10 by 10 grid, and you can't repeat any digit on any long row, on any long column, or also on any one of these little 3 by 3 squares. That's the bit that we don't have in a Cayley table. We just have the rows and the columns. So it's not really Sudoku. It's really what mathematicians call a Latin square. A Latin square is a square of objects, elements in it, in which there's no repetition on any row or on any column. Right? But that the elements are all chosen from the same set. Right? So in this example, A, B, and C. All the elements in here are A, B, and C, and we're not repeating any element on any row or on any column. So let's just finish playing the Sudoku-like game to complete this table. So now that I know that A is okay right here, what about the entry underneath it? Well, I have a C on the same row, so it can't be a C. I have an A on the same column, so it can't be an A. But that still leaves me the room to put a B here. And that doesn't violate my Sudoku, right? I still have no repetition of any element on this column, no repetition of any element on this row. And so the only thing that could go wrong at this point is trying to fill in this last empty circle. Well, I have a B and a C already on its column, so this can't be B or C. I have a B or a C on its row, so it can't be B or C. Fortunately for us, we still have one choice left, and that's to put an A in that slot. So now we have a complete Cayley table. We've filled in all the entries. And this Cayley table satisfies that no element is repeated on its row or on its column. And so the left cancellation property or the right cancellation property is not going to tank the differences between the elements in this group. And secondly, we can verify every element has an inverse. So if the identity element is called A, then the inverse of A is A. So here's A living on its row. The inverse of B is C, because B operates C is equal to A. And the inverse of C is B, because C operate B gives me A. And so in this case, we were able to come up with a Cayley table that meets all of our criteria to be a group. We didn't check associativity. That would take a little bit longer to do. So we're just going to leave that one, again, as an exercise. But if we have associativity, then we have closure, because all these elements are from my set ABC. We have an identity, namely A. We filled that in first. And every element has an inverse. B has a unique inverse C. C has a unique inverse B. The other thing that we notice about this system is that the group that we've made is Abelian. This Cayley table is symmetric, which is to say that each of the elements that's not on the diagonal is equal to its mirror image across the diagonal. So that B and that B reflect the fact that BA is equal to AB. This C and this C reflect the fact that CA is equal to AC. And so on for the rest. CB is equal to BC. And finally, I guess that's it, right? Because every element commutes with itself, as we'll talk more about next week. AA is equal to AA, BB is equal to BB, CC is equal to CC. But we have a symmetric Cayley table. And so the group that we made is Abelian. So the two key observations here is that there was only one way. We were forced by the definition of a group into making the choices that we made in finishing this table. As soon as I chose A to be my identity, then I was forced into putting a C here, as we saw, because we tried the other possibilities, they didn't work. And as soon as I had a C here, that means I had to put the A over here, so that we didn't, again, repeat an element on a row or on a column. And as soon as I had a C and an A here, that also defined these last two elements, again, because we can't have any repetition in their columns. So there's only one way to do this, and the way in which we did it turns out to give us an Abelian group. So the answer to our questions is yes, we can make a group out of this, and in only one way that gives us an Abelian group. So the way that a mathematician would state this result, just to get some lingo on top of it before we move on to our next problem adventure, is we would say there is, so is where this yes is coming into my statement, there is a group, but there's only one. There is a unique group. And you might have an objection to this, because we did make a choice along the way. But let me finish my sentence. There's a unique group of order 3. Right? Order is something we're going to start talking about next week. Order of a group just means how many elements are there in that group. So if I want a group of order 3, a group with 3 elements in it, then there's only one way to make a group that has this structure. And then we might add to that by saying, and it's Abelian. All right, so at this point you might object. I hope you object a little bit, because I've just made the claim that there's only one way to do the process that we just did. But you'll say, didn't we make a choice right here? When I decided to single out A as being my identity, isn't that a material choice? If I had chosen B to be my identity instead, would we have gotten something different? And that's the question that I'm hoping that we're wrestling with today in our class, is what does it mean for one group to be the same as another group? If I just change the label for my identity element, so that now maybe I'm calling my identity element B instead of A. So I'm going to keep my order for my elements. Well, I'm going to keep my identity element in the first row in the first column. So if I change it so that now B is my identity element, do I have something different? So then I would have to come in here and change all these products again. Right? I would get B times B is B, A, C, right? Because B is my identity element now. So its row and its column are just repetitions of the header row and the header column. But then this new A is like my old B, where when I did B times B is equal to C before, it was the only way to go forward. So now A is the new B. A operate A has got to be C. And that forces me to put a B here. That forces me to put a B here. Forces me to put an A here. But if you take a look at this Cayley table and the Cayley table from the previous example, everything is in the same place that it was before. The only thing that we've done is we've just changed the names of the elements. So we haven't changed the behavior. We've only changed the labels that we place on the names of the elements in my group, which is a bit like taking my set of elements and just placing the B before the A instead of the A before the B when I write the set of my elements, right? But that doesn't change the set of elements, right? The sets don't care what order we write their elements in. And if we're really doing abstract algebra, then it shouldn't matter what labels that we put on the elements in a group. What matters is the structure that those elements make when they operate on one another, using the operation in our group. So my claim is that if I chose B to be the identity instead of A, and I did the rest of my process, which again, there's only one way to do, right, that this Cayley table and the Cayley table we started with look different at a first glance, but they're telling us about the same algebraic structure. Because all we've done is we've changed the labels on the outside of the row and the column. We've just said A is the new B, B is the new A. And so the really interesting question in abstract algebra is, what happens if you give me more elements? If you give me 4 elements, how many different ways are there to make a group? If you give me 6 elements, how many ways are there? If you give me 12 elements, how many ways are there? It turns out, for example, that if you were to give me 101 elements, giant bag, 101 Dalmatians in it, and tell me to make a group out of that, that first of all, it's possible. I can do it. I can make you a group of order 101. What's less obvious is that there's, again, only one way in which I can do it. And I'm certainly not going to go through all the Cayley table argument to show you why, which is why over the course of the semester we need to get more sophisticated in how we think about the elements of groups where we might not be able to write down all of their elements, or we just don't want to because there's too many. And we might not want to use a Cayley table because it would be gigantic, right? So it turns out there's only one group of order 101. It also ends up being abelian. But why that is a whole semester length kind of question. Because to answer that kind of question, we'll come all the way back to the fundamental theorem. It's called the fundamental theorem of finite abelian groups, which is really the capstone of our semester. So we've got a lot of time to work our way forward to that. All right, so there's sort of 2 things that I could do next. And I think the one that's going to be more useful, because either one of them is probably going to take the rest of our time together on the live stream today. But I think the one that's probably more valuable at this point is to get us back into proof land a little bit, because the other option is to start working with matrices, and that can wait a little bit. Let's hone our proof skills. So I want to write a proof, and the proof is going to be of the following proposition. So let me just get the proposition on the table. I'm calling it a proposition because it's not quite profound enough to be a theorem, but it's certainly interesting. So the proposition is as follows. Let G be a group. And so anytime I say let at the beginning of a proposition or a theorem, that means that this is the thing that all of our proofs will take for granted. Right? So we don't have to treat this as part of a hypothesis. All of our proofs, whether they're direct proofs or indirect proofs or contradiction, contrapositive, whatever, all of them will begin from the premise that G is a group. So now let me write the if then. Okay. So if for all elements of my group, let's call them X, if for all X and G we have X squared is equal to the identity, so I'll write E for the identity element of my group. So that's my hypothesis, the antecedent in my if-then statement. This, by the way, is the same as saying that all elements in my group are their own inverses. We've seen some examples already in the groups that we've studied of elements that are their own inverses. For example, reflections inside of a group of symmetries. Every reflection is its own inverse, because when you do it twice, you end up back to where you started. So you can think of this as being like a proposition about reflection-type elements, except that what we have in this proposition is a group all of whose elements are reflection-like. And now what's the conclusion? The conclusion is G is an abelian group. So there's my proposition. It says that if my group is made up of only reflection elements, reflection-like elements, things that are their own inverses, if this is true for all of my group elements, then we'll be able to draw a very strong conclusion about the group, that it must be an abelian group. So how in the world are we going to prove this? Well, again, like we talked about in the live stream last time, and I like this metaphor so much that I want to keep using it. Proofs come in 2 steps for mathematicians. And the first step is exploratory. The first step is throwing a bunch of stuff up at the wall to see what sticks. And very often this takes the form of scratch work on a whiteboard, chicken scratches on the back of a napkin at the bar, that kind of stuff, right? And that is the environment in which no holes should be barred, right? There you don't want to be constrained by form or communication or complete sentences or any of that kind of stuff. You just want to try some stuff and see if you can find a lead into what you're trying to prove. The second phase, of course, is once you have found that lead, then you need to actually write out a proof that's carefully, logically sequenced and is appropriate for the audience that's reading it. Okay. So I know that writing proofs in a quiz or an exam setting sort of requires you to be thinking about both of these at the same time because the time is limited. But when you're working on proofs in the comfort of your own home, do yourself a favor and don't even start writing a proof until you've finished working out exactly what it is that proof is going to contain by writing it on the back of a bar napkin or something, right? So here we go. Let's see if we can figure out how to do this. First, I'm looking at this if-then. So if for all x and g we have x squared equals e, then g is abelian. And it feels to me like it'll probably be easier for me to start by assuming that the purple thing is true, assuming the antecedent, the hypothesis, which would mean that if I'm successful in figuring out how to turn that assumption into a deduction that g is abelian, then my proof is going to end up being a direct proof, where I begin the proof by saying, assume that this purple thing is true, we want to show that this green thing is true. So let's do the exploration. So here's the back of my bar napkin. So I'm just going to kind of write here. Assume that x squared is equal to e for all x. And I'm kind of saying to myself, I want to show that G is an abelian group. So that means that I need to remember, as carefully as possible, what is the definition of abelian group. So on my bar napkin, I'm going to kind of write up here in the corner, G is abelian if and only if, for all G and H in my group, the order of operation doesn't matter. GH is equal to HG. I'm using the juxtaposition. I don't have a symbol for my operation this time because I don't want to keep writing little circles and stuff. So just imagine GH is what we get when we operate on G with H. So my burden of proof is that thing that I've just written down there, that for all G and H, we need to be able to show that GH is equal to HG. All right, so what's that going to take? So this is the thing that I must prove. This is my burden of proof right here. So that's going to be my want to show. So maybe I'll write that somewhere next to it also. Want to show this. And because my want to show is a universal statement, it begins with the clause for all G and H. That means that what I ought to do is start by choosing 2 G and H's. So let G and H be elements of my group. Okay. And because it's for all, I don't get, as the author of this proof, I don't get to be specific about what G and H are. I don't get to say, for example, oh, let's suppose that G is the identity, or let's suppose that we're in a group of integers mod 5, and let's let G equal 3. We don't get to be specific, because we don't have the choice. The universe has handed us a group, and we know nothing about what that group is. And in order to deduce this statement, the universe is also handing me elements G and H in my group, and I have no control over what those elements are. So all I know is that they're elements of the group G. And I've assumed that every element of the group G satisfies that the square is equal to the identity. So when I was working out this proof a little earlier today, kind of how I did it was I'm thinking of this as a process where I want to know how to get from there to there. How do I get from GH to HG, showing that they're equal, and using along the way this assumption, right? Because if I haven't used that assumption, then it sounds like what I just proved is something that would be true for all groups, and we know that it's not true for all groups that G is abelian. So let's play around. This is really all that I did. This is what happens on the back of bar napkins. So if I play around with this a little bit, I might say, well, okay, so what do I know about G and H? They're elements of the group. But I've assumed that every element of the group is its own inverse. So for example, G squared is going to equal the identity, and so is H squared. Right. Again, because that was the assumption that we made. We're setting ourselves up for a nice direct proof. So I might try something like, all right, what if I were to take and multiply by G? Well, if I multiply by G once, I've changed this expression. But if I multiply by G twice, that's the same as multiplying by E, the identity element. Right? And that is a transparent operation because of the identity property for groups. So what I might try, and again, this is the phase in which you're just kind of throwing ideas up against the wall to see what sticks. So this is the same as GH, GG, because GG is the same as E. So I might just write that as an intermediate step. GH, GG. And there I'm using the hypothesis, right? The hypothesis that every element in this group has its square equal to the identity. All right, but that doesn't seem to have gotten me close enough to where I'm going. I'm going to try to make this expression into HG. I at least have an HG hanging out inside of my thing now. But it's got an extra G on the right side of it. It's got an extra G on the left side of it. And because we can't assume that our operation is commutative, that means that we can't get that leftmost G and the rightmost G together. If we could get them together, then all we would do is just slide one of these G's all the way to the front. We would have a G squared, it would cancel, and we would have HG. But that's what philosophers, logicians call begging the question. You are begging the question when you're trying to use the conclusion that you're trying to draw as part of your argument, right? If at some point in my proof I either explicitly or tacitly make the assumption that our operation is commutative, then I've immediately failed in my job to prove this thing. I've begged the question. When you're making a logical deduction, you are not permitted to use your conclusion that you're trying to draw as part of your argument. Okay? So I can't just slide this G up to the front of the line and then cancel it because G squared is equal to E. I've got to try something else. Let me make a little bit of space here. G, H, G, G. All right, so at this point, we've used the self-inverse property for the element G. Right? We've applied the assumption here to the element G to help to make our argument. We haven't yet applied it to H. So when I was working out, on the back of a piece of paper today how to do this proof, I said at this point, well, let me see if I can sneak an H squared in here somewhere. I could try to sneak it here at the end, or I could try to sneak it here at the beginning. And I ended up deciding on the beginning, but I tried it the other way first. So maybe you'll see why when I write down this next step. So what I'm saying here is let's stick an identity out on the left side of this expression, which again, that's transparent. We can put an identity there if we want to without changing the element that we're talking about because of the identity property. But then we can replace that E by an H squared, which I'm just going to write as H times H. So there again, we're applying our assumption that every element in this group is its own inverse. And now you might say, well, all you've done now is make an even bigger mess, right? Because we started out with GH. That was just a product of two elements. We introduced a third element, which then became 4, which then became 5, which now became 6. So I've made my expression much more complicated than it was. But now is the time to kind of look at the expression that we have and realize that we won something. Namely, we won the fact that where we're trying to go has an h at the beginning and an h at the end. Now our expression has an h at the beginning and an h at the end. Right? But then the question is, what's going on in the middle between the h in the front and the g at the back? I have hg, hg. Well, that's got a nice rhythm to it, doesn't it? Because G is by assumption a group, and groups satisfy the associativity property, that means that I can, as the author of this proof, decide to put parentheses around that pair of HGs that I have here in the middle. And now I can make the final step of the argument, which is, can I make those HG disappear? Well, HG, by the closure property, is an element of the group, right? Because any two elements of my group, if I operate on them together, I get another element of the group. So HG belongs to G. And all elements in my group satisfy x squared equals the identity. So all elements are their own inverses. And so namely, HG is its own inverse. Therefore, with the role of x being played by HG, we can conclude that this product is the identity. And so what do I have? I have HEG, and by the identity property, that's HG. So that scratchy mess is what the back of my bar napkin looks like. But it seems as though this sort of clever trial and error line of reasoning has gotten us exactly what we want, right? We were able to show that GH was equal to HG, and we actually 3 times explicitly invoked this assumption along the way. We first did so by applying it to G, right? G times itself is equal to E. We then applied it to H, HH is equal to E. And then the third time, which was sort of unexpected, right? This just arose in the course of our argument. We also applied it to the element HG. HG is equal to the identity. And that got us home. So let's close up the live stream today by turning this bar napkin into a proof. So the first thing we want to do in any proof is to clue our audience into the form of the argument. And because on the back of my napkin I was able to successfully make the direct argument, assume the purple statement, and we deduced the green statement, let's make that clear to the reader up front. So in the margin I'm just going to write here, we're going to signal to the reader that this is going to be a direct proof. And the way to do that is by assuming the hypothesis. So assume that for all elements x in my group, we have x squared is equal to the identity. So assume every element is its own inverse. And then if you want to, you can write here, we want to show G is abelian. Some authors will do that, particularly if you're still growing into your proof skin. It's kind of a good way to remind yourself of what's happening in the rest of the proof. It signals the reader what the burden of proof is, right? It says, once you see that I have shown that G is abelian, then I've proved this proposition. But as you get more advanced in mathematics and you read more advanced authors, often they won't write this step here. They'll just leave that for the end. Therefore, G is abelian, right? And so actually, I'm going to write it at the end also. Therefore, G is abelian. Because we know that our last line of the proof is that. Let's put the QED marker here optimistically, and then we'll fill in the rest. All right, so we want to show that G is abelian. And here's where we need to know what the definition of abelian is. Not only the definition, but also very carefully quantified definition. Right? G is abelian if and only if for all G and H in the group, GH is equal to HG. So I'm going to write that one line above my conclusion here, because that's the burden of proof now to show that G is abelian. Thus, for all G and H in my group, we have GH is equal to HG. And again, that is also not something that every proof author is going to write explicitly. They might rely upon the reader to remember what the definition of abelian is. But for us, we're still sort of, again, growing into our proof skin and getting used to using definitions very carefully and precisely. I'm going to write that there. Now, our burden of proof is the universal statement for all G and H in my group. And so I need to begin my argument up here by letting the universe choose for me a G and an H. So let G and H be elements of G that are arbitrarily chosen. Get used to that arbitrarily chosen phrase, by the way. That's a useful indicator for the reader that we're about to make a universal argument. What we're about to say will be true for any G and H that anybody could possibly pick. That's where the arbitrary comes in. Right? Anybody can pick these G's and H's, and the argument that we're going to make needs to hold, no matter what choice was made for those. Slide this over just to make some more space. So let G and H be arbitrarily chosen. That's what's going to make this the universal claim that we're about to make. All right, so now is the time for us to reproduce this magic. That's the other nice thing about what happens between the bar napkin and the finished page, is that you probably had to do a lot of messy trial and error to get here. But by the time it lands in your proof, it almost looks like divine inspiration, right? Which is exciting for the writer. It's less exciting for the reader, unless the reader, especially if the reader is trying to learn something from that proof. Because very often the choices that we have to make and the different trials and errors that go into the discoveries that you make on a bar napkin, those all happen behind the scenes. And so when you read a proof that was written by, a really insightful mathematician, it can look as though, it's just divine inspiration. Like, how did they think to do that? And usually the answer is a whole lot of bar napkins. So let's go. We need to show that GH is equal to HG. And we're just going to reproduce this line of reasoning, just annotating it along the way with the justifications that we're using. So the first thing that we did was put an identity element, the identity element, on the right side over here. And then we turned that identity element into G squared. And how we knew that we could do that is, again, because of this assumption, right? So we'll make explicit reference to that assumption. So let me write this right next to it. By assumption. And I'm going to kind of write here in parenthetical, x equals g. And put a little asterisk here and next to the assumption to indicate that that's where the assumption is coming from, right? Don't be shy of using these by phrases, by assumption, by construction, by definition, by theorem, by corollary. Those are the keys to how mathematicians bring evidence into the courtroom of a proof, right? To justify why this statement must be true. It must be true because we have assumed that all elements in my group satisfy x squared equals e, and therefore because g is one of the elements in my group, it satisfies this equation also with g in place of x. So g squared is equal to e. Okay. Now we go back to the napkin and say, what was my next step? I added in an e over here on the left-hand side. So let me add that in here also. E. If we wanted to be super brutal, we would also say by the identity property for groups, but I think I'm going to not write that here because I don't have a lot of space. But so we introduce the e on that side, and then we turn that e into a pair of h's, h squared, g, h, g squared. And there again, we've used that same assumption. I'm going to write that on the left side this time, by assumption. With the role of x being played by h this time. And therefore h squared is equal to e. And then comes the last bit of magic, right? It was this regrouping step. This is h times hg, I'm going to write that as hg squared this time, just because I'm running out of room. And the reader will understand, unless we want to remind them, that that's the associativity property at work. But then the last step is that hg quantity squared becomes the identity. And that just becomes hg. And again, it's an occasion to remind the reader why that last step is the case. It's by that same assumption, with the role of x being played by hg. Whew. And that's it, right? And when you come to read this proof from beginning to end, again, it looks like magic, right? Assume that every element is its own inverse. We want to show the group is abelian. So we choose two arbitrary elements g and h. And because they're chosen arbitrarily, we're going to meet the universal claim burden of proof. Right? And then we do this manipulation. We throw an identity on the right side, we turn it into a g squared. We throw another identity on the left side, we turn it into an h squared. We regroup and discover an hg quantity squared in the middle of my expression that then also goes away because hg is an element of the group and therefore is its own inverse. Thus, for all g and h in my group, we have shown that gh is equal to hg. And that's the very definition of G being an abelian group. So this is the kinds of arguments that I want you to get accustomed to discovering and then to making. So on your homework problems in particular, take the extra time because it's really good practice. Once you've found your discovery, don't just... So I could have, if I was rushing through my homework, I might have stopped right here and said, okay, great, done. Right? But that's not going to help you to grow as an author of proof and as a communicator of mathematics. It really takes that extra step to say, all right, now how do I take this mess, this hot mess on the back of a napkin, and how do I turn that into a proof that's suitable to communicate to other mathematicians who weren't in my head when I wrote this stuff on the back of a napkin, why this thing must be true. So you're not going to submit a bar napkin to an academic journal. You will submit a proof that looks something like this to an academic journal for publication. So we're going to wrap up today's live stream there. The next places that we're going to go is we're going to start pulling in some notions about finite groups. So if I have a finite set of objects, how do I make a group out of them, and how many different ways can we do that, and what can we learn about groups that have finite numbers of elements from looking at their structures. So I'm looking forward to doing that all with you, but let's bring this live stream today to a close. Thanks for joining us, and we'll see you next time.